Okay, ladies and gentlemen, welcome to today's trigonometry class. And today we're going to continue to work with trigonometric ratios and trigonometric functions, but we are going to look at special right triangles. Now, give me 1 second while I acclimate myself and I can actually text the topic that we're going to be discussing in this video. So the topic that we're going to be discussing in this video is evaluating trigonometric functions for special angle measures. So evaluating trigonometric functions for special angle measures. Evaluating trigonometric functions for special angle measures. Now, to recap, we've been working with the 6 basic trigonometric functions: sine, cosine, tangent, secant, cosecant, cotangent. And we said that, for example, the opposite of the tangent was the cotangent, and the opposite of the sine was the cosecant, and the opposite of the cosine was the secant. But today we're actually going to work with special right triangles. More exactly, we're going to see, or more precisely, we're going to work with 45, 45, 90s, and 30, 60, 90. So looking at a 45, 45, 90, we know that this would be our 45-degree angle. Let me erase that real quick. Sorry for that. 45-degree angle. And of course, we have our 45-degree angle here. And we know that the sides of a 45 are x, and x times the square root of 2, although your textbook has it expressed as the square root of 2x, which is the same thing. X times the square root of 2, or the square root of 2x. And the other triangle that we have, which is the the 45, the other one that we have is the 30, 60, 90. And let me graph that one here, and that way we'll go straight into the first example. So the other one is the 30, 60, 90, and the 30, 60, 90 and we'll have x times the square root of 3 or the square root of 3x, which is the same thing. The hypotenuse, which is 2x, and x, which is down here, which of course is opposite of the 30-degree angle. So this is 30. Remember that the x is always opposite the 30-degree angle, and the square root of 3x is, and the square root of 3x is opposite the 60-degree angle. So technically the shorter leg is always opposite the 30-degree angle, and the longer leg is always opposite the 60-degree angle. So we're going to work with these triangles again. Now we're going to go straight into example number 1. And example number 1 of your textbooks, which is on page 35, says, evaluate the 6 trigonometric functions for an angle that measures 30 degrees. Okay, so we're actually, let's see. Perfect. So I'm going to go ahead and erase. No, I'm actually going to see if I can. Yeah, I'm going to go ahead and erase this. The 45, 45, 90. And then let's work with the 30, 60, 90, which is on page 35 of your textbooks. Okay. So the 35, again, we have our 30-degree angle, which is here. We have our 60-degree angle. We have our square root of 3, and we have our hypotenuse, which is 2 times x. So let's look at example number 1, and the problem says, evaluate the 6 trigonometric functions for an angle that measures 30 degrees. 30 degrees. Okay, now we know the 6 basic trigonometric functions because we worked with them before. And let me just, okay. So we know the 6 basic trigonometric functions because we worked with them before. So that means that we're going to look for the 6 basic trigonometric functions of the 30 degrees. So that means we're going to focus on this one here. And we need to understand that in this case, x is our opposite because it's the farthest from 30. Okay, so it's very important to understand what angle we're looking for, because in the previous examples we just had z, but now we don't just have z, we have them giving us specific values. And of course, the x times the square root of 3 or the square root of 3x is the adjacent, because we're looking at the 30-degree angle. So if we want to know, for example, the value of the sine of 30 degrees, let's say we want to know the sine of 30. The sine of 30 is opposite over adjacent, or excuse me, is opposite over hypotenuse. So we say that the sine of 30, the opposite is the x. Okay, since the opposite is the x, we say x, and the hypotenuse is 2x. We say the sine of 30 equals x over 2x. Again, the sine of 30, the opposite is the x, the hypotenuse is the 2x. Now, what's going to happen here is that technically there's a 1 in front of this x, so technically this is 1x, right? And what's going to happen is that the x's are going to cancel out, and the answer is going to be 1/2. So the sine of 30 degrees is 1/2. Now, the good thing about the triangles like the 30, 60, 90 and the 45, 45, 90, the special triangles or the special right triangles, is that the measurements are not going to change. So the sine of 30 will always be 1/2, okay? It's not like when we work with other angles that are not special angles that we're going to see a little bit later on. Now we have to find the cosine of 30. So remember, the cosine of 30 is adjacent over hypotenuse. So that would be x times the square root of 3 over 2x. Over 2x. And what's going to happen here is that, again, The x's are going to cancel out. So this is going to cancel out. So is this. And my answer is going to be the square root of 3 over 2. So we say that the cosine of 30 is the square root of 3 over 2. Square root of 3 over 2. The square root of 3 over 2. So that's what the cosine of 30 would be. The cosine of the square root of 3 over 2. Now if we're going to look for the tangent of 30, okay? So the tangent of 30. The tangent of 30, we know is opposite over adjacent. So the tangent of 30 is opposite over adjacent. Now, opposite over adjacent. So opposite is x because it's the farthest from 30, and adjacent is x times the square root of 3. So we're going to say x, which is my opposite, over x times the square root of 3. And what's going to happen here is that they are going to cancel each other out. And x over the square root of 3, and x cancels out. And that would leave me with 1 over the square root of 3. And I have to rationalize my denominator. So remember that when I rationalize the denominator, I'm multiplying everything by the square root of 3. And also by the square root of 3. And of course, when I multiply the square root of 3 by the square root of 3, I'm going to finish it down here. down here. The square root of 3 by the square root of 3 is the square root of 9. Let's see if I can, you know what? Let me just see if I can move this around a little bit. Okay. So what's going to happen here is I'm going to multiply the square root of 3 times the square root of 3, which is going to equal to the square root of 9. I'm going to write it down here. Then you're going to multiply 1 times the square root of 3, which is the square root of 3, right? And because 9 has a perfect square root, which is 3, we say that the tangent of 30 is the square root of 3 over 3. Okay, so again, all I did was x, which is opposite over x times the square root of 3, which is adjacent. The x's cancel out, and that leaves me with 1 over the square root of 3. So I rationalize the denominator, and I simply multiply everything by the square root of 3. So 1 times the square root of 3 is the square root of 3, and 3 times the square root of 3 is the square root of 9. The square root of 9 equals 3, and my final answer is square root of 3 over 3. So those are the first 6 trigonometric functions. Now I have to find the first 3, excuse me. Now I'm going to find the other 3 trigonometric functions. Okay, so I'm going to go ahead and erase this real quick. So I found the first 3. Now I have to find the other 3. Let me see if I can. Oh, never mind. Okay. So I have to find the other 3. Let me erase this. This is example number 1 on page 35 of your textbooks. And then we're going to do example number 2. And that would be the end of this video lesson. So the other 3 basic trigonometric functions. Now your book uses the identity functions, and we can do that. So I want to find the cosecant. The cosecant of 30. Now the identity function is 1 over the sine of 30. 1 over the sine. Okay, 1 over the sine. We're going to use the trigonometry, the identity functions, although we can also use the, and I'm going to do both variations just to compare that they're the same, but it depends. Sometimes they'll want you to use the identity. Sometimes they'll want you to do something different. So I know that the sine of 30 was 1/2, so I would say 1 over 1/2. And 1 over 1/2 is basically what I'm going to do is dividing, or I'm multiplying by the reciprocal, so it would actually be multiplying 1 by the reciprocal of 1/2, which is 2 over 1. So whenever you're dividing a fraction, remember you're multiplying by the reciprocal, so all I did was I multiplied 1 times 2 over 1, and that would be, well, 1 times 2 is 2, and 2 divided by 1 is 2, so my answer is 2. So the cosecant of 30 degrees in this case is 2. If I want to find the secant of 30 degrees, the secant of 30 degrees, the secant of 30 is basically the opposite. If I use the identity functions, is basically the opposite of the cosine. So that'd be 1 over the cosine, right? So 1 over the cosine means that I'm going to say, well, the cosine of 30 was the square root of 3 over 2. So 1 over the square root of 3 over 2. And remember, I'm going to multiply by the reciprocal. So I'm going to multiply 1 times 2 over the square root of 3, which is actually going to be 2 over the square root of 3. But because the problem is asking us to rationalize our denominator, that means that I'm not done with it yet. And I have to actually just say, well, 2 over this, I have to rationalize the denominator, so that I have to turn that into 2 over the square root of 3 times the square root of 3, because I'm rationalizing my denominator. And basically the same thing that happened in the other example, the square root of 3 times the square root of 3 is the square root of 9. Again, this step can be done mentally, but just so you guys have an idea of what's happening. So again, the square root of 3 times the square root of 3 equals the square root of 9. 2 times the square root of 3 equals 2 times the square root of 3. The square root of 9 is 3. So my final answer for the secant of 30 is 2 times the square root of 3 2 times the square root of 3 over 3. 2 times the square root of 3 over 3. Okay? And that's my answer for the secant. Now the cotangent, and I'm actually going to erase this one. Let's see if I have some space down here. So the cotangent is the opposite of the tangent. So if we use our identity, we say 1 over the tangent of z, 1 over the tangent. Okay, so we would just plug in the numbers. We found our tangent because our tangent of 30 was the square root of 3 over 3. So we say 1 over the square root of 3 over 3. And I'm actually going to erase this right here so I can have the extra space. Okay, so if you got a little lost, you can always rewind the video and look back at that exercise, but I'm going to erase it just because I need the space. And if I kind of clump everything together, it can cause confusion. So let me just go ahead and erase this. Okay, we're looking for the cotangent. We know that it's 1 over the tangent, and we know that our tangent is the square root of 3 over 3. So what we're going to do now is just invert, and this would be 1 times 3 over the square root of 3 which indicates that 1 times the square root of 3 is the square root of 3 is 3 over the square root of 3. So now I have to rationalize my denominator. 3 over the square root of 3. Now, the good thing about this is because these are special right triangles, the tangent is of 30 degrees is always going to be this answer and the sine and the cosine, they're always going to be the same numbers. They're not going to change because they're special right triangles. When we work with other angles that we're going to see, like again, I mentioned, and we're going to see later on, there would be different methods. Anyway, well, 3 times the square root of 3, you guys should be getting used to this by now, is the square root of 9. And 3 times the square root of 3 is 3 times the square root of 3. The square root of 9 is 3, so I'm going to actually finish it down here. And 3 times the square root of 3 stays expressed. So the cotangent is actually 3 times the square root of 3 over 3. 3 times the square root of 3 over 3. And that would be the answer here. Give me 1 second, guys. Just making sure that I wrote everything correctly. Let me erase something here. And oh, excuse me, ladies and gentlemen. Let me make this simpler for you guys. I just realized that there was a mistake. So 3. Let me rewrite this because it doesn't look that well. So this is the square root of 9. And this would lead to 3 times the square root of 3 over 3. And what's going to happen here is that I can just basically divide 3 by 3. So, or cancel the 3's out, which is basically the same thing. And that would leave me with the square root of 3. So the cotangent of 30 degrees is actually the square root of 3. So let me explain that real quick. So for the cotangent, I know that I have 1 over 3 over the square root of 3, which means I have to multiply by the reciprocal, which means that this would turn into 3 over the square root of 3. 1 times 3 over the square root of 3 is 3 times the square root of 3. In other words, itself. I'm going to rationalize the denominator, and then again I multiply the square root of 3 times the square root of 3, which is the square root of 9, and 3 times the square root of 3. The square root of 9 has a perfect square root, which is 3, and then that will leave you with 3 times the square root of 3 over 3. Now what happens next is I just cancel out the 3 and the 3, and that will leave me with the square root of 3. So the cotangent is the square root of 3. Now on to example number 2 real quick. And in example number 2, we're going to use a 45, 45, 90 degree triangle. And again, we're being asked to find the 45, 45, 90 degree triangle. Okay, so we have, or we're being asked, excuse me, to find the 6 basic trigonometric functions. So we have our same situation, guys. We have x, we have x, we have the square root of 2, and we have a 45 degree angle here, and we have a 90 degree angle here, and we have a 45 degree angle here, and we're being asked to find the 6 basic trigonometric functions. So we'll start with the sine. The sine of 45 is, now here's the thing with the sine and the cosine of 45. they're going to be the same answer because 45, 45 is what we call an isosceles triangle, which means that two of the angles or two of the sides and two of the angles have the same measurement. So it really doesn't matter which one is opposite or which one is adjacent. They're going to be the same thing. So if we're looking for the sine of 45, we say x over the square root of 2 over x. Excuse me, guys. X over the square root of, or times the square root of 2. So we would say 1. So the good thing is that we're going to do this once, and then that's pretty much it. We don't really need to do anything else. So we say x over x times the square root of 2. And let me just fix this x. It doesn't really look that well done. Okay, so what's going to happen is the same thing. Technically, this is a 1x. So this x is going to cancel out with this x. And that's going to leave me with 1 over the square root of 2. But I have to rationalize my denominator. So that means I have to multiply this by the square root of 2 and the square root of 2. So guys, what's going to happen is that, well, 2, the square root of 2 times the square root of 2 is going to be the square root of 4. The square root of 4. And 1 times the square root of 2 is the square root of 2. And the square root of 2, or the square root of 4 is 2. So my final answer is going to be the square root of 2 over 2. And that is the sine of 45 degrees. And because 45 degrees is an equiangular triangle as well, or an equilateral and an isosceles, excuse me, because it's an isosceles triangle. That means that two of its sides and two of its angles have the same measurement. So that means that the cosine of 45 is also the square root of 2 over 2, because again, it doesn't matter which side is opposite, which side is adjacent. They're the same number. So this would be the square root of 2 over 2 as well. And to find the tangent, well, it's opposite over adjacent. Tangent is opposite over adjacent. Tangent is opposite over adjacent. So that would mean x over x, which equals 1. So the tangent of 45 degrees equals 1. Now, we found the first 3 trigonometric functions. Now we're going to find the other 3. But in this case, I'm not going to use the identity. I'm actually going to use just writing the opposite, because technically writing the opposite and writing the identity functions is going to give you the same answer. So for 30, 60, 90, we saw us using the identity functions or the reciprocal identity functions. But here we're just going to use the opposite. So we know that if I'm looking for the secant is the opposite of the sine. So the secant is the opposite of the cosine. So if we know that the secant is the opposite of the cosine, okay, or 1 over the cosine, however you guys want to do it, we know that secant, instead of saying 1 over the cosine, instead of using this function, 1 over the cosine, I'm simply going to say that the secant is the same thing as saying adjacent over hypotenuse. And here's the thing. If I find the secant, I also have the cosecant, because the cosecant is the opposite of the sine, right? So we'll see in a minute. The adjacent over hypotenuse. Okay, so let me explain this again. The function says that the secant is 1 over the cosine, and the cosecant is 1 over the sine. And in our previous example, you saw me use the identity functions. And in this one, I'm going to show you a variation of it. Now, the cosecant is the opposite of the sine. So 1 over the sine, I can say the cosecant is 1 over the sine, or opposite over hypotenuse. And since, again, 45, 45, 90 is an isosceles triangle, which means I have two sides that are the same and two angles that are the same, the cosecant of 45 is also going to be the secant of 45. Now, for the secant, we have 1 over the cosine, or we can say adjacent over hypotenuse. It really is the same thing. That's why they're called reciprocal functions, okay? Because I can just turn them upside down. So adjacent over hypotenuse. Now, how does this work? Well, very simple. Again, if I find one, whether the cosecant or the secant, I have the other because this is an isosceles triangle. So let me just find the cosecant. So instead of using 1 over sine, I'm going to say it equals opposite over hypotenuse. Now, the opposite of 45 is, is the adjacent over hypotenuse. I wrote it backwards, excuse me. Let me fix this. It's supposed to be hypotenuse over opposite. Let me fix that. It's supposed to be hypotenuse over the opposite. Hypotenuse. I just realized I made that mistake and I could have created a lot of confusion. So let me erase this as well. And let me fix that. So the cosecant is 1 over the sine, or the hypotenuse over the opposite. And here it's the cosine, which is opposite. It's the opposite of the cosine, which is opposite over adjacent. Now I have this done correctly. I apologize for the mistakes. Okay. So, meaning I can use the identity function of 1 over cosine, 1 over cosine, or 1 over sine, sine, excuse me. Or I could use the function 1 over cosine to find the secant, or 1 over sine to find the cosecant, or I can simply use the opposites. So again, and I've said it for like the 5th time, because this is an isosceles triangle, it doesn't matter, because if I realize 45 in an isosceles triangle, two sides are the same and two angles are the same. So that means that if I find the cosecant, I automatically have my secant. Okay, so let's find the cosecant. Instead of using the 1 over sine, I'm simply going to say hypotenuse over the opposite. So I'm going to say x times the square root of 2 over x. Over x. Okay, so x times the square root of 2 over x. Now, what's going to happen there is I have x. Excuse me, ladies and gentlemen. I have the square root of 2 over 2. And excuse me for a second, ladies and gentlemen. Seem to be having trouble with my internet today. So let's see if I can fix this a little, or work this out a little better. I apologize for the delay. So I know that the sine is the hypotenuse over the opposite. So I can say x times the square root of 2 over x. Or I can say 1 over the sine of 45. So the opposite, the hypotenuse would be x times the square root of 2 square root of 2 over 1x or x, because it's the opposite, okay? And what's going to happen here is that the x is going to cancel out with the x, and that leaves me with the square root of 2 over 1, which equals the square root of 2. And of course, if the 45, 45, 90 degree triangle is isosceles, meaning two sides are the same and two angles are the same, if the cosecant of 45 is the square root of 2, that means that the secant of 45 also equals the square root of 2. And to find the cotangent, it's really easy as well, because the cotangent is the opposite of the tangent. So instead of saying 1 over tangent, I can simply use the opposite of it and say, well, it would be, if tangent is opposite over adjacent, this would be adjacent over opposite. And adjacent over opposite, in this case, well, I have x over x. Let's see if I can finish it down here. I have x over x, which equals 1. So the cotangent is also 1. Equals 1. And let me box that in down here. Okay, that didn't work. Okay, so the cotangent equals 1. And that would be the answer for the cotangent of 45, okay? Now, I use simply inverting the functions around. You could also use identity, and in fact, let me show you real quick how it would have looked like if I used the identity function. So let me just erase this right here. So this is what, if I don't use, all I did was, instead of, to find the cosecant, instead of using 1 over sine, I used the opposite, or the reciprocal, which is hypotenuse over opposite. The hypotenuse is the square root of 2. The opposite would be x. The x's cancel out. That leaves me with the square root of 2 over 1, which equals the square root of 2. To find the cotangent, it's opposite over adjacent. Again, it would just be x over x, which equals 1. And that's where I got the answer for 1. But what if I had decided to use the inverse, or the other identity function, in order to solve the problem? What would have happened? Well, you would have had something like this. It'd be a longer process, but it would give you the same answer regardless. So if I would have decided to use 1 over the sine of 45, I would have said, let me use a different color. Let me use a different color to explain this. So that way, if I would have decided to use the identity function like they did in your book, I would have just said 1 over the square root of 2 over 2 over 2. And I would have just had to invert it. And remember, 1 times 2 over the square root of 2, which is what happened in your book. And that would be 2 times the square root of 2, which means I have to rationalize or the denominator and then multiply everything by the square root of 2. And that would just be 2 times the square root of 2 over the square root of 4, because remember that the square root of 2 times the square root of 2 is the square root of 4, which would have led to 2 times the square root of 2 over 2, because the square root of 4 is 2. And then you would have to just cancel this out, and your answer would have been the square root of 2. So this step is just longer. And of course, when we talk about other topics in trigonometry, you're going to see this, step again. But you could just very easily just flip it upside down or reciprocate it. So guys, this is it for this video lesson. Hopefully this video will be of good use to you. If you have any doubts, you know where to find me. So I'll see you soon. Bye.